Thank you, Dean. It's really a pleasure to be here. And let me just clarify, my talk today is going to concentrate on the chemistry of chelating agents and how they apply to all fields of imaging, not just nuclear medicine or MRI. So the topics of discussion today, and I hope some take-home lessons that we can get out of this. We want to review ligand metal complexes in general, specifically what the key elements in consideration for in vivo applications are. Talk about the importance of stable chelates in the thermodynamics and the kinetics, which we talk about this a lot, but it's always important to remind ourselves of this. Types of chelating agents. Talk a little bit about some imaging modalities that depend on chelation chemistry. Choices of metals and ligands. What kind of information do we need to get from the combinations? And what does the future look like? And then we'll end the talk with a couple of examples on targeted agents and physiologically responsive agents. So just to define ligands and chelates in general before we go too far, a ligand is defined as any anion or organic molecule that donates a pair of electrons to a metal ion. And one of the simplest models you can think of is cisplatinum, where we have 4 monodentate ligands bound to platinum. And of course, when we start to talk about chelates, we start to talk about linking these ligating groups together. And this is an example of a 2 monodentate ligands and 1 bidentate ligand. And they can continue to get more and more complex as we start to put all of the ligating groups within one molecule. So now we have an example of a tetradentate ligand with NTA, and with EDTA we have a hexadentate ligand. Multidentate ligands of this type bind by displacing solvent molecules from to form the ML complex. And so when we talk about multidentate ligands, we're talking about chelating agents, and chelating agents is derived from the Latin word claw. So the resulting ML complexes are always referred to as chelates. So these are just general principles. And there are a ton of complexes that I'm sure you've seen in the literature, and these are just examples of some very standard things that we usually see. So popular multidentate ligands that are used for chelating metal ions, I've shown a group of the macrocycles that are clearly some of the most popular and well studied ligands in science in this area for the last 20 years. We have specifically DOTA, which everybody is aware of. DOTA has been a paramount and important ligand for contrast agents, for nuclear medicine. We also have a number of other larger macrocyclic structures like this that are well looked at for copper. We have smaller ones that work well for gallium, and we have very rigid structures that form very inert complexes with copper. And then we have complexes like PCTA, or ligands like PCTA, which can also be used to make luminescent derivatives. The acyclic ligand systems are well studied too, and there is many examples of these, not only in diagnostic agents, but in therapeutic agents. And in a minute we'll talk about bifunctionals. But we've seen DTPA and DTPA derivatives where we change the rigidity of the backbone. And more recently, we've seen some more exotic ligands, and exotic only with respect to their use. Deferoxamine has received some attention over the last 6 years because of the emergence of zirconium-89 as a useful PET imaging isotope. And we'll talk about that a little bit later. And some of the work that, Some of the work that Martin Breckbeil has done over the years was to look at pendant groups off of various types of chelating agents to increase the stability. And indeed, these are some very novel ones as well that are being developed further. So when we talk about chelating agents, as I mentioned, the important thing, especially for targeted diagnostics and therapeutic applications is the fact that we have to be able to attach them to things or modify ligands so that they target. And so there are a plethora of let's see if I can. There's basically a plethora of these bifunctional ligands out there that are designed for various types of attachment. We have attachment through side chains, and we have basically three different kinds of connection devices. One of them is a connection using isothiocyanate, connections using activated esters, and so these are standard types of bifunctional chelating agents. And we won't talk about all these today, but I will spend a fair amount of time talking about the principles behind thermodynamics using DOTA as an example. A very important part of the equation when you start to think about combining ligands and metals, especially for imaging purposes, one of the most popular and well-studied methods, modalities, of course, is MRI, and we use gadolinium mostly for this application. But there's a lot of other lanthanides that work well. The main thing here is that we have to remember the types of characteristics between ligands and metals. And so with the lanthanides, we know we have 8 coordinate geometry, and we have to pick ligands that work well for that. PET isotopes, the popular ones are copper, gallium, and yttrium. Zirconium is a new one, and I like zirconium because it has such a long half-life, and we'll talk a little bit more about that. But these are all important things to look at when you're deciding on ligands. You've got to think about the architecture of the ligand and the isotope that you're using and the half-life, which I put in red here because that is an important feature to remember. So factors to consider in the design of ligands for various metal applications. Selection of the ligand donor atoms, we mentioned that briefly, but what does that actually mean? So we use an old principle in inorganic chemistry that's been around for a long, long time. It's matching hard acids to hard bases and vice versa. And sometimes you hear this terminology and it's not always clear exactly what this means, but basically remember that all metals are Lewis acids, all ligands are Lewis bases. Hard means something that's got a lot of charge density to it, basically. So anything that makes a high charge density is considered hard. Soft means that it's the charge density is dispersed. And so very simple principles, but if you remember those and you look at your ligands and you look at your metals, it's easy to kind of work out the process of matching them up. The coordination number, as I mentioned, is really important because you can't do anything about it. The metals dictate the kind of coordination that they want. So you have to keep that in mind, and if you have a metal that prefers hexadentate, you need to use that kind of geometry in the design of your compound. The role of the ligand architecture, cyclic versus acyclic. What do I mean here? So with this, when you think about macrocycles, we have an interesting thing here. They have size selectivity that's very precise. The cavity size defines exactly how big a metal or how small a metal is going to go into the cavity. And this is very pre-organized, and this is different than acyclic ligands. Acyclic ligands have enough flexibility that they can adopt geometries that have a greater breadth of what they can complex, but it doesn't mean that they make better complexes. The basicity of a polyaza donor scaffold is a critical component of the overall stability of complexes, and that's something to keep in mind because a lot of this information is in the literature, and you can look it up before you go blindly into designing something. The kinetics of making the complex, the formation and the dissociation, that's incredibly important and often overlooked in the design of all complexes. So remember this, acyclic ligands are flexible and structures and they form complexes pretty quickly, but they also dissociate equally quickly. whereas macrocyclic ligands, they form their complexes slowly, but long term their stability is higher and they dissociate much more slowly as well, and we'll talk about that in greater detail. So just to point out the size selectivity matching and how important this is, if we look at two of some of the most well-studied ligand systems, DOTA and DOTA, we know that, for instance, that gadolinium is a great match for DOTA. But when we look at the thermodynamic stability measurements, so we see 24.7 for DOTA, and we see 14.3 for NOTA. Oh, that's an obvious thing related to the match, because if we switch over to a smaller radius metal, which is in this case gallium is perfectly matched to the cavity size of NOTA. It's not such a good fit for DOTA, but it still works. I want to talk about thermodynamic stability and conditional stability. And we'll do it at kind of a high level because I don't want to get bogged down in too many of the details. We can get the principles across fairly easily. But basically we're concerned with that reaction, the reaction of the metal with the ligand to produce a complex. The issue here is that this definition is in the literature, and it defines this ratio at an unusually high pH, where in fact there's no protons included in this equation. And we know that polyasa macrocyclic backbones are highly basic and they get protonated. Now, for that reason, we need to define this at a slightly different way, and we define it by calling it a conditional stability constant. Conditional stability constants are typically reported at pH 7.4 to give you a better idea of what's going on. And why I point this out is at pH 7.4, most of these highly basic ligand systems have some degree of protonation going on, and so the ratio down here reflects all these different species that are actually present. So when you see this number, it looks a little bit different than what we would call a thermodynamic stability. I want to just point out that it's very easy to predict the overall thermodynamic stability of a potential complex by looking at the sum of the pKa's of the nitrogens in these rings. So basically this is a plot of the thermodynamic stability versus the total summation of the pKa's in the macrocyclic backbone. So this has been around for a long time, and it's an easy tool to use, and it also reflects the idea that these nitrogens are easy to protonate as well, since they are so basic. Now let's just touch on the idea of kinetics of complexation with lanthanides, and I'm going to use DOTA as an example here because it's a real classic. So basically now we're talking about making a complex with a ligand that's protonated. So DOTA looks like this in water at physiological pH, and I think I'm not sure if I can quite point to it, but you'll notice that there's two nitrogens that still have a proton. These are highly basic nitrogens in this compound, and they don't want to come off easily, so basically we have two positive charges trapped in the cavity. So when we add the metal, really what happens first and instantaneously is the association of the metal with the anionic portion of the molecule of the ligand. And so this happens fast, and now if we had an acyclic system, it could do a lot of flopping around and rearrangement, and those protons would come out easily, but they don't in these kinds of compounds. So there's an energy barrier here, and we usually overcome that by heating it up a little bit. And once those protons pop out, then the metal falls in place and we have a very, very, very stable complex, and that's what we're after. So thermodynamic stability basically says, what does the complex look like when thermal equilibrium is attained? Kinetic stability says, how fast does the complex reach that equilibrium? This is the part that oftentimes gets overlooked. So here's a simple model, a cartoon, if you will, that describes 4 different situations. The red line and the blue line show 2 complexes that have a very low thermodynamic stability. We're looking at, on the y-axis, free metal being given up by the complex. The main difference here is that look how long it takes for the line, the blue line, the complex that's blue, to get to that thermal equilibrium. This is an important feature. In the bottom, we have 2 very stable complexes thermodynamically. One has it reaches its equilibrium very rapidly. One of them doesn't. One of them reaches the equilibrium very slowly. And at the end, we have 2 very good complexes down here, but they have different kinetics. So, again, let me reemphasize, this is important, very important, because now we have many compounds out there that the thermodynamics are very low, but yet the kinetics are so slow that on the time frame of a biological experiment, it may be negligible. So, what I'd like to do now is take all this information that we've talked about and kind of go through the model of all the contrast agents that have been developed over the last 15 years. This is a list of all the commercially available contrast agents on the market. I've listed them in rows of ionic and non-ionic. And the interesting thing here is, if you note, we have not only macrocyclic compounds that are showing, in fact, let me just mention, I've included both of the conditional stability constants and the thermodynamic stability constants here for comparison. But basically, what we see here is a group in the ionic form that are very stable. They show very good log K, both thermodynamic and conditional. But when we go down to the non-ionic ones, what happens? When we go down to the non-ionic ones, we start to see a drop in this log K. And so what does that mean exactly? Does that mean these are bad complexes? And does this mean these are bad complexes? And so we need to look at that a little bit more carefully. And there's been a lot of work done on trying to understand this and elucidate it over the last few years for reasons related to instability in some of the complexes in these contrast agents. So this is an experiment where we take the preformed complex, we put it into a buffered solution of phosphate buffer at pH 7, and we also add a zinc as a competitive ion. When metal comes out of the complex, it's irreversibly precipitated by the phosphate, and so we'll see, basically what we're looking at is a relaxivity here, and as the metal is removed from the complex, the relaxivity drops off. So this is a in real-time look at what stability, kinetic stability. So we're looking at kinetic stability, and we'll notice all these DOTA compounds, even though we saw differences in the conditional stability constants, what we see is they maintain, this is kinetic stability, so it's taking a very long time for this to be observed. So in this time frame of a real experiment, that's insignificant. On the other hand, we see real differences in the kinetics with the acyclic systems. So, and these 2 in blue are still very good. But when we start to get down this low, we start to wonder, is that the right, is that good or not? So I just bring this up because it's a very important part of chelation chemistry for whatever you're doing. In fact, the DOTA complexes are so stable that we have to do things that are completely artificial to see differences in them. So we take them down to pH 1.2 and measure a conditional stability here, and then we see huge differences. Are they meaningful? Probably not. Obviously they're not, because we looked at them on the previous slide. We also see that the linear analogs, some of the linear analogs can't even be detected at these kind of pHs. They're just non-existent. So important to remember, and this was said by Mike Tweedle a long time ago, as well as many of the other leaders in this area, High thermodynamic stability constants measured in water aren't neither necessary or sufficient conditions for predicting the in vivo stability of any chelate. And so this is worthy of remembering. So molecular imaging architecture and aspects to contemplate. And I just throw this out because I thought of it. I thought it was interesting. Radionuclide-based complexes. When we're thinking about them, what comes to our mind? Well, the thing that comes to my mind is I remember that the metal functions as a signal beacon only. So mostly then it's not affected by the environment. Any targeting properties are going to be introduced by conjugating to some sort of a magic bullet or modification of a customization of a ligand. We have exquisite sensitivity, but the experimental window is determined by the radionuclide half-life. So on the other hand, paramagnetic complexes, the metal functions as a signal beacon, but it can also be coaxed into giving you more information by modulating its response to various environments such as pH enzymatic activity. Targeting is the same. I mean, we still have to have some kind of a targeting mechanism. Sensitivity isn't as good, but adequate, and we're learning more and more different ways to get around some of the problems related to signal to noise. The experimental window is determined by the residence lifetime of the complex. And there are quite a few lanthanide metals to choose from, all of which have different kinds of properties, all of which are being explored for different applications now. I want to talk about a couple examples, and I'll talk about the zirconium one because this is most interesting to me. Antibody-guided immunoconjugation with zirconium is possible only because of the long half-life. It's been hindered for PET because antibodies takes a long time to localize in a target, so short-lived isotopes don't work too well. So this is one of the first examples of a long-lived isotope used with a monoclonal antibody, and in this case it's metastatic breast cancer, and the top image is an MR showing some metastatic sites in the vertebrae and one in the brain. The bottom one is the superimposed PET imaging with the trastuzumab, which is a HER2 sensitive indicator, and it definitely points out those lesions, but it also pointed out this lesion in the brain as being HER2 positive. So that's kind of a lot of new information to get out of a combination of an MR and PET. And so this is, in my opinion, this is an exciting kind of new area for PET imaging. The last example I'd like to talk about is from Professor Sherry's lab. This is very interesting to me because it builds on the fact that we start off with an MR contrast agent based on gadolinium, and we build a couple of receptors in here that can actually complex zinc as well. And why zinc is of interest is beta cells, when they're stimulated by release of glucose, they are influx of glucose, they release insulin, and in addition they also release zinc. So this makes this compound valuable if it can sense zinc. So the concept is kind of simple, but the discovery wasn't. So basically what we have is when two equivalents of zinc are formed or introduced into this complex, it binds strongly to human serum albumin. And what's the effect of this? Well, before HSA is available to it, the relaxivity is there's kind of a modest improvement by adding just zinc, so about 5. But when it sees HSA, this thing triples by it's 3 orders of magnitude higher, so we get a 165% increase in relaxivity. So that's a big deal because that kind of change in sensitivity can actually be detected. So the model that that was developed was this. And so basically, here's our chelating agent. When the insulin is released from the pancreatic beta cell, it quickly picks up 2 equivalents of zinc, it binds to HSA, and it lights up. And this is actually a working model in vivo as well. So this was published in 2011 by Dr. Sherry's group. Very cool because here, adding that complex with no additional glucose introduced, we see very little activity in the pancreas. But including glucose in the injection, then we get all kinds of activity showing up. This is a kind of an important discovery. It has a lot of implications. So it reflects the design and capabilities that are available with these different kinds of chelating agents. So I hope from this discussion, the take-home knowledge might be that we refreshed our minds on what the simple principles behind acid-base chemistry are related to chelates and ligands, and understanding the differences between the different types of macrocyclic ligands that are available to us, and the kinetics and the very, very important keys that have been around for a long time. But again, I reemphasize that we need to keep them in mind, and understanding thermodynamics and kinetics. So these are the main things today. If you pick those up, I'm really happy. And I want to thank, I have way too many collaborators to even begin to thank, but of course Professor Sherry's been my mentor and friend for a long time, and most of the things that I've learned in this area have come from my interactions with him. So thank you.